Good evening, everyone, and thanks for taking time out of your busy days to join us for this webinar. My name is Martina Dorigo. I'm a dairy scientist at AHDB Dairy, and I'm delighted to bring you tonight's webinar on the role of fiber in the dairy cow. This webinar is proved very popular with over 100 registrations from dairy farmers, vets, nutritionists, consultants, and researchers. Our speaker today is Professor Liam Sinclair from Harper Adams University, who will present the results of an AHDB-funded project on the role of functional fibre in the dairy cow diet in a UK context. The project was part of the AHDB SRUC Grass and Forage and Soil Research Partnership. I would also like to mention Usama Tayeb, who, supervised by Professor Liam Sinclair, completed his PhD under this project. A little housekeeping before we start. Liam will run through his presentation, which will take around 35 minutes, and there will be time for comments and questions at the end. You will all stay muted throughout the webinar, but if anyone would like to ask a question, then please type your question into the box on the left-hand side of your screens. I will ask Liam your questions at the end of his presentation. If for time reasons we can't answer them all, you will get a reply by email in the next days. We will aim to finish up within an hour, and tonight's presentation will be recorded and will be available to watch back on the AHDB Dairy YouTube channel. Also, we will endeavour to keep this webinar running as smooth as possible, but please bear with us if we encounter any technical difficulties. We will try to keep this to a minimum. Some information about the speaker. Liam Sinclair undertook a degree in agriculture with animal science at Aberdeen University before moving to the University of Nottingham, where he completed a PhD on rumen metabolism. He then moved to Harper Adams University as a lecturer, progressing to Professor of Animal Science in 2010. His research interests focus on dairy cows and include improving the health attributes of milk, increasing forage utilization, improving mineral nutrition, and reducing the environmental impact of dairy cows. He was awarded the Sir John Hammond Prize in 2011 for his applied research in ruminant nutrition and his ability to transfer research findings to industry. In 2016, he was elected as the president of the British Society of Animal Science. So, without further delay, Liam, it's over to you.
Okay, thank you very much. Hopefully everybody can hear me okay, but if not, then please type in and let Martina know. So I'm going to spend the next 30-35 minutes or so speaking about the role of fibre in dairy cow nutrition, and also highlighting some of the research that we've been doing and some of the practical messages that you can take home and hopefully apply on your particular dairy farm. So if we look at a little bit of a background, then milk yield has been increasing pretty constantly over the last 30 or 40 years at around about 100 kilograms per cow per year, pretty unrelenting regardless of production system. But most of this increase in milk yield has been obtained from either feeding more concentrates or improvements or higher quality forages, and have resulted in lower dietary fibre levels. And a consequence of that is that we are potentially exposing the cows to an increased risk of metabolic disease. And these metabolic diseases include subacute ruminal acidosis, or SARA for short, but easier to say. Also, too low a fibre content can result in displaced abomasum, can be associated with milk fat depression, which is particularly important if you're paid on a composition basis, and can also reduce fibre digestion and reduce how much energy we get from the diet. If we focus on this subacute ruminal acidosis, or SARA, just for a few minutes, then if we look at what's happening within the rumen, and it is the rumen that we're focusing on, so the first chamber within the digestive system of the dairy cow, where all the food, the forage, the concentrates go in and get fermented by the rumen microbes. And the optimal pH within the rumen is between pH 6.2 to 6.5, so a pretty neutral pH. And we generally consider SARA is when the rumen pH drops below round about 5.8. Now, the consequences of this low rumen pH is that it can reduce intake, can result in diarrhea, and you can view this in terms of very wet fecal material, perhaps bubbly, undigested grains coming through, and decreased milk production. Can also result in the absorption of toxins from the rumen, and that can result in an inflammatory response, and that in its own right can affect dairy cow performance. If we look at some surveys that have attempted to quantify how much SARA is a problem in dairy farms, then if we look at those across Europe and North America, and this includes grazing systems with more Irish type cows, New Zealand type systems, all the way through to North American diets, then the incidence ranges from about 11 to 24%. And the cost of that, due to all the factors that I mentioned previously, can be somewhere between £90 to £350. So for a typical dairy farm, it's somewhere between £1,000 to £12,000 that SARA may be costing. However, the definition of SARA is somewhat problematic. Most people would say that it is when pH occurs below 5.6 for at least 3 hours per day. Other people would say that pH 5.8 for 5 to 6 hours per day. But there is considerable variation in the pH within the rumen, and the measurement of on farm of rumen pH is particularly difficult. Now, there are a number of different ways we can do that. So here we've got using a stomach tube, which can be used to take a rumen sample. But it's got problems in that often within the rumen, we've got a mat of fibre, and sometimes this tube simply sits on top of that mat and doesn't penetrate into the rumen. A number of vets can take a ruminocentesis, and that simply means taking a needle and inserting it through the flank of the cow into the rumen, taking out a small amount of rumen fluid, which you can then analyse for its pH. But obviously that's only from one site within the rumen at one particular point in time. More recently, we've got the advent of rumen pH boluses. They tend to sit in a section of the rumen called the reticulum, which generally has a slightly higher pH, but is expensive, can fur up over a period of time, but does provide us with a means of a non-invasive means of measuring rumen pH. Generally, they cost somewhere between £350 to £400 per bolus. So if we consider the fermentation within the rumen, then we've got the fermentation of carbohydrates. So by carbohydrates, I mean sugars, which we can have in grasses or in molasses, starch in the form of wheat or barley, or within something like whole crop wheat as a forage or maize silage, and fibre, which we have as part of the cell wall within forages and other feeds. And when they're fermented within the rumen microbes gain so much energy from it, and then they produce acids. And these acids lower the rumen pH. And the rate of acid production is dependent on a whole variety of different factors. It depends on how much starch and sugar we have in the diet, and I'll be coming back to that a bit later, but also the form that it's in. So if it's very finely ground, it'll be fermented a lot more rapidly. Can also be affected by acids in the silage. So we know that when we get the silage analysed, that we've got a variety of different acids, of which lactic acid is the main one, and that is introduced into the rumen as the animal eats it. All feeds have got some form of buffering capacity, so legumes such as red clover or white clover are more resistant to a change in pH. And of course, the amount and form of fibre in the diet, which is what this particular talk is going to be focusing on. So all of these factors here are relating to how much acid is being produced or introduced into the rumen. So what keeps the pH up if all these acids are being produced? Well, the main thing is to do with phosphate and bicarbonate buffers. Now, a proportion of these buffers comes in through the saliva. Not all of it, round about half of it comes directly across the rumen wall as the acids are being absorbed, but round about half is introduced via the saliva. So if we can increase the eating and ruminating time, then that in theory will increase saliva production, and these buffers maintain the pH and keep the pH within the optimal range that the rumen microbes want. But the difficulty from a dairy cow point of view is that the amount of saliva isn't related to rumen pH, and the cow doesn't control her rumen pH by salivating more. She doesn't detect that the rumen pH has got lower and she needs to salivate more. How much saliva she produces is simply based on what we feed her and how long she eats and how long she ruminates for. And I think this is quite nicely demonstrated by the next piece of work that I'm looking at here. And this is looking at the forage to concentrate ratio and the saliva production litres per day. So this is looking at 4 different forage to concentrate ratios. So here, a high concentrate diet, so 40% forage, 60% concentrates, going up to 70% forage and 30% concentrates. So a high concentrate based diet up to a high fibre based diet. And then we've got the amount of saliva that's been produced by eating and ruminating. Then we've got resting, so the cow still produces saliva even though she isn't eating and ruminating, and that gives us then a total daily production. And you can see that as we increase the amount of forage in the ration, then we increase the amount of saliva, which will help to keep the pH up. But as she's eating and ruminating more, she's got less resting time, and that decreases. So the total amount that's produced is increased with a higher forage ration, but the amount is comparatively small at around about 5% or so. And as a consequence, then we have a lower rumen pH here, even though we've got more saliva being produced and quite a high amount of saliva being produced with this high concentrate-based diet. The amount of acid is greater, and that is reducing rumen pH. So we can see here that the total amount is not affected by as much as what a lot of people would assume it would be. The ruminating time increases with forage particle length. We know that if we give a longer particle length in the fibre, that cows will ruminate more. But the amount that reaches the maximum is actually quite small, and studies that have been done would say that there's really not a lot of benefit above a forage particle length of around about 10 millimeters. If you get below that, then you will get an effect on how much ruminating time the cow spends. But if you go much above that, it doesn't really have a major effect. Eating time, however, is more affected by particle length, and if you give a longer material, cows will tend to spend a bit longer chewing it before it actually gets into the rumen. So how does fibre fit into that? Well, if we consider a healthy rumen function and performance, then we need to consider what we call the non-forage carbohydrates. So these are things such as the sugars and starch. Both are concentration in the diet and how finely ground they are and presented to the rumen. We've also got the fibre concentration of a ration. So if you look at your grass silage or maize silage analysis, then on that you'll find something called neutral detergent fibre, NDF, and that's a measure of how much fibre is in that particular feed. NDF, quite simply, is a bit like you taking your t-shirt after a hard day's work and putting it in a washing machine along with some detergent, and you wash it up within that. The detergent makes all the grease and all the dirt and all the protein solubilize, and what's left is really just the cotton fiber particles in your t-shirt. And that's what this chemical analysis does here. This tells us how much total fiber or neutral detergent fiber is present in the diet. And the thing that I want to be focusing on is this bit here, which is the forage particle length. So we can have two different diets with the same amount of fiber in them, but if one has got longer fiber in it compared with another, how does that affect rumen metabolism and ultimately cow metabolism and cow health? So what we're speaking about is really a balance in terms of rumen pH. We've got fiber here, both the content of fiber and also the forage particle length on the one side, and then on the other side we've got the starch content in the diet and how it's presented, and we have differences between starch sources. Wheat, for example, is much more rapidly broken down within the rumen than something like maize, and if we grind the wheat, then it is even more rapidly broken down. And we've got sugars, which are very rapidly broken down and available to the rumen microbes. So what happens if we have too long a particle length? Well, firstly, it makes ensiling difficult, and that's quite an important point, and I'll come back to this later, that a shorter particle length makes compaction within the clamp easier, and that can improve the fermentation characteristics. And that in its own right can affect dairy cow intake and subsequent performance. Too long a particle length can also decrease feed intake, particularly in younger ruminants, but can also have an effect in larger dairy cows as well. And a consequence of that can be a decreased milk production. However, a longer particle length is generally associated with a higher milk fat content, and we'll look at what situations that can have an effect in a few minutes. If, on the other hand, we have too short a particle length, then that makes the production of the acids within the rumen that we were speaking about a few minutes ago that much more rapid. It can also decrease rumination time, which can decrease the amount of saliva that's produced. And a consequence of this increased acid production and decreased saliva production is a decrease in rumen pH. It can also increase rumen passage rate because it can flow out of the rumen more rapidly, and that can result in a decrease in fibre digestibility. And if we look at here, the particle size in the ration, so this is from a couple of studies here, looking at the particle size in millimeters in the overall ration and the amount of ruminating time, minutes per kilogram of dry matter intake, we can see that we have a straight line relationship here. But we also need to bear in mind that these are quite short, and we'll come back to that when we look at UK diets a little bit later. So certainly if we've too short a particle size, we get less ruminating time, and that can affect rumen pH. Okay, so we've spoken about the chemical composition, and we've spoken about forage particle length. How do we combine these two into something that we can use on farm? Well, this phrase called physically effective fibre has been developed, and it is there to try and combine the physical attributes of the diet and the forages with their chemical attributes or the NDF content. So we look at the physically effective content within the diet, and we generally do that using a series of sieves. Now, there are a variety of ways of doing this, but the most popular is to use what's called a Penn state separator. And this is a Penn state separator here. Each one of these sieves is roughly 1/2 meter by 1/2 meter. We've got 4 sieves here. This would be 19 millimeters, this would be 8 millimeters, 4 millimeters, and then a base pan down at the bottom. So if you put your forage or your total mixed ration on top of that, and you shake it and you rotate it and shake it again, do that several times, then you'll end up with a distribution over these different pans. And that can tell us how much physically effective fibre there is. And if we multiply that by the fibre content, then we can end up with this new term called physically effective NDF. And that's to try and tell us how much of that fibre is going to affect rumen metabolism and rumen function. Now, there's been various discussions as to what level we should use, between 1.18, 4 and 8 millimeters, but somewhere between 4 and 8 millimeters is what most people would use. So for example, if your diet has got 40% NDF in it, so that's the combination of the forages and the concentrates, and 50% of that diet, when you shake it down, 50% sits on top of this 8 millimeter screen here. So 50% physically effective here over the 8 millimeter screen, then that will be a physically effective NDF content of 20%. Okay, so with 40% fibre, but only 50% of that fibre is considered to be physically effective and alter rumen function and saliva production. So this is a proposed relationship here between physically effective fibre. So remember that 20% from the previous example, and this is going from about 10% up to about 30 or 35% dietary physically effective NDF. And here we've got daily rumen pH and we've got dry matter intake. And we can see that as we increase the dietary physically effective fibre, we go from a low rumen pH, susceptible to SARA at this point here, up to a higher rumen pH at around about 6.2. But we don't really have much of a benefit after that the rumen pH remains at that level. So having a higher physically effective NDF doesn't seem to have a beneficial effect on rumen pH. In contrast, if we end up with a very high physically effective NDF, say at 25%, then that can reduce dry matter intake from somewhere, in this example, from 23 kilograms of dry matter down to somewhere such as 20 kilograms of dry matter. So too much physically effective NDF can reduce intake, and that of course will reduce milk production as a consequence. So we have a balance here between trying to maintain rumen pH versus maintaining dry matter intake and milk yield. Now, there's been quite a number of studies conducted in this over the last 20 years or so, but most of these studies have been undertaken using North American type diets. Either they've been conducted in the United States or Canada or in Europe, but they've generally been looking at North American diets based on maize silage and lucerne, rather than some of the wetter grass silages that we have in the UK. So we wanted to find out, are the current recommendations suitable for the UK, and can we use what the North Americans have been doing, or do we need to have something a little bit different? So we went on to 50 commercial dairy herds throughout the UK, so going from Dumfries down to the southwest, quite a cluster here in the Midlands. All were feeding grass silage. 34 of the herds were also feeding grass silage with maize silage. The milk yield was about 9,200, so reflective more of house cows. This was over the winter time that we did this, so we chose herds that were feeding partial and total mixed rations. Herd size was above the UK average, but milk fat was comparable to what most farmers would be looking for. How do we measure the particle size? So PS here meaning particle size. Well, we also used a pen state separator. So these are the 4 sieves that I mentioned previously. So the base pan, 4, 8, and 19. But we thought that we'd probably need a larger sieve size because we had a feeling that most UK rations and forages would be higher. So when you shake it out, then this is the sort of distribution that you get. So this would tend to be your concentrate components down at the bottom, and here you've got quite a lot of forage up at this end here. So we developed this new pan to allow us to characterize UK rations and forages. We went out onto farm and quickly realized that this one wasn't large enough, that we needed to make some more. So we went back and we made a 44 millimeter and then a 60 millimeter screen to try and characterize some of the dairy cow rations and forages that were being fed. On the 50 farms, we also looked at some feeding practice, and I think it's perhaps interesting to look at some of these. Feed delivery per day was somewhere between 1 and 2, so some farms are feeding twice a day, but most were feeding once a day, so the median was 1. Feed push-ups per day, most farms were 4 times. The maximum that one farmer claimed was 16 times, and the minimum was 1 push-up per day. Feed removal per week was on average 5 times. Some farms did it every day, so 7 times per week. One farm only did it once per month, so only removed refusals once per month. Feed space per cow was on average 61 centimetres, but anywhere between 76 and 30. Quite an interesting component was the length of the feed mix minutes. That ranged from about 5 minutes up to 60 minutes. Although most farms mix for around about 15, but quite a bit of variation there. So we'll come on to the range in forage particle size of grass and maize silage in a minute. But one of the practical aspects that you can use this pen state separator for on farm, and a very simple one, is to tell you 2 things. Firstly, how well mixed the ration is. And to do that, you take samples from a feed face immediately after the forage mixer wagon has dispensed. And if you take it, say, at 3 different points along the feed fence, then you look at the particle size distribution. You'd expect it to be the same at those 3 points. If it's not the same at those 3 points, then it indicates that the diet is perhaps not very well mixed. The other thing that you can do is come back after a period of time. We did that after 4 hours, and take a sample from those same points again, and you can run them over the pen state separator. And if the particle size distribution is different to what the original values were when the ration was fed out, then that would indicate that there is some degree of sorting going on. So we did this for 50 farms. And what we found was that around about 58% of herds had got poorly mixed rations. So what was presented, for example, at the end of the feed phase was significantly different from what was present at the beginning of the feed phase. And around about 66% of herds had got significant diet selection after 4 hours. So when we went back after 4 hours, the particle size distribution was different than when we originally measured the feed. And perhaps equally of concern is that on just over a third of the herds, there were no feed refusals. So the animals were effectively being underfed and not provided with sufficient diet. Now, the consequences of these are that you can have a very well formulated mixed ration, but if cows are coming out in the morning hungry because there hasn't been enough feed, and it's a poorly mixed ration which they're able to select from, then you'll find that there's quite a variation there in what individual cows are eating. And that, of course, can put those cows at risk of SARA. So that's the first take-home message. Make sure that your rations are well mixed and there isn't diet selection. Moving on to the mean particle size. So this looks here at the number of farms here and the mean particle size here. So using that Penn state separator, we can do a little bit of maths and work out what the mean particle size of these were. And this is off the maize silage here, so the individual forages. And we can see that there's a bit of variation, but most are coming out at between 9 to 11 millimeters. That's the average particle size of maize in the UK. If we compare that with North American values, and here this is some work looking at that. So this is again looking at the North Americans who only use these 4 different sieves here. Then you can see that whilst there's a little bit of a variation there between 8 to 19, generally we're quite similar to what North Americans have in terms of their maize silage. We're a little bit wetter than what they have, which may mean that perhaps we're not getting as much coming out in the bottom sieve, but nevertheless the profile isn't drastically dissimilar to what North Americans have. In comparison, if we look at grass silage, then whilst there are some short silages, none of them were as short as what the maize silage was, and most were coming out in this 40 to 45 millimeter range here. And if we compare that with North American values for lucerne silage, or more haylage in terms of the dry matter that they look at, so this isn't grass silage, but lucerne haylage from North America, then we can see that we've got quite a radically different profile here. Most of our material is sitting on top of this 19 millimeter sieve, and very little is coming down below. So the major difference between UK and North America is over our grass size particle length. And we'll look in a minute to see whether that is important or not. So that's the individual forages. When you look at the mixed rations, so this is the mixed rations here. So this is looking at North American guidelines, so Penn State guidelines here for how much should be above the 19, the 8 to 19 and less than 8 millimeters. And this is the values that we found for UK grass silage-based total mixed rations and UK grass and maize silage-based rations. Then you can see that we are quite radically different, mainly because of this grass silage longer particle length. So the grass silage is more different than what the grass and maize silage is. So why do we have particularly long grass silage in this country, and is it important? Well, part of the reason why we feel that UK grass silage is so long is that we obviously perhaps have a greater variety of harvesters, both in terms moving from self-propelled precision chop forage harvesters through to forage wagons and even big bales, although there were no big bales in our particular survey. We tend to spread and row up grass much more than what we would do with lucerne. And if we look at maize, for example, it tends to be presented to the cutting mechanism in the forage harvester in a more consistent manner than after we've spread grass silage and tedded it out and rowed it, which we do to try and increase the dry matter content. We also feed quite a lot of concentrates in the parlour, which is quite different to North America. And therefore it may be believed that perhaps we need to have longer forage as a consequence. And there's also some concern that if you have particularly wet grass silage, that too short a chop length may result in clamp slippage. and that's something that AHDB are currently looking at. And obviously the belief that if you have too short a grass silage, that can result in subacute ruminal acidosis. Now, although we went on to 50 farms and the data was quite noisy, we did actually find a relationship here between the mean particle length of the diet. So this is the diet mean particle length here and milk fat content. So even under practical farming conditions, you can see that there is an effect here of the particle length. And also in terms of milk yield, not such a strong relationship, but this is looking at a longer particle length here, is increase in milk fat content, but is associated with a lower milk yield. So what we spoke about earlier, we were managing to get from our data. So having looked at what was happening on commercial farms in the UK, we decided that we would follow up on some of these points and decided to focus on grass silage because that's where we felt most of the variation was. Maize silage was similar to North America, but the grass silage seemed to be quite different and is the major component in most of our dairy cow rations. So we decided to look at the effect of chop length of grass silage when it was either fed alone or along with maize silage. And when I say alone, obviously there were also concentrates that were fed with them as well, but around about 55% of the dry matter was from the forage. So either grass silage alone or a mixture of grass and maize silage. So with 2 chop lengths of grass silage, what we've called a long chop length, although in reality that was round about the mean value from the samples that we had determined from our survey, or the short chop, which was within the shortest 5% in the UK. We then fed at 2 forage ratios, either grass to maize silage of just grass silage, or a 40-60 grass silage to maize silage on a dry matter basis. Now, one of the consequences of a shorter chop length is that you will have a different fermentation profile, and that can affect the cow performance in its own right. So the dry matters of our grass silages, well, they're actually quite wet at around about 20%, and the crude protein, CP crude protein here, was around about 12%. The pH wasn't that different, but there's quite a bit more lactic acid in the short chop grass silage. So it's important to bear in mind that you can often get a better fermentation, better consolidation in the clamp with shortcut grass silage. So we then mix that to provide us with our 4 diets. So this is the long grass diet, the short grass diet, the long grass with maize diet, and the short grass with maize diet. The dry matter content was less with the grass silage-based rations because they had a lower dry matter content of the grass silage, but the protein content was similar across our 4 diets. Our physically effective fibre, this was way above what previous research from the United States would say would be necessary and should result in lower dry matter intakes. But our long maize and our short maize was still quite high values and at the upper end of what most people would recommend. So we introduced rumen pH boluses. So these are about the size that you'd have of a typical trace mineral bolus. We put them into the rumen, and this just shows a typical trace here. So this is when it's introduced, and then you can see this pattern going on here as the cows generally eat, increases, and then they get fed in the morning and eat again. So you get this kind of fluctuation going on here, but it measures the pH at round about every 15 minutes or so. It's important to bear in mind that these boluses reside in a section of the rumen called the reticulum, and that means that the pH values are around about 0.2 above what you'd expect in other areas of the rumen. So these values are always a little bit higher. So although that's 6.5, if you were to measure it in other areas, it would be down about 6.3. So when we looked at that in terms of the rumen pH, and this is our long grass silage and our short grass silage, so this is the change in rumen pH across time of the day. We fed at around about 9 in the morning. So you can see that the rumen pH is increasing, then it's coming down to reach its minimum value at around about 6 at night before it starts to increase again. But there was no difference between the short grass silage and the long grass silage. It wasn't affecting rumen pH in the slightest. The maize-based rations were lower in rumen pH, but again, there was no effect of the particle length of the grass silage within that. In terms of cow performance, then decreasing the chop length increased intake by around about 1 kilogram dry matter per day. So this is our grass silage, our long grass, our short grass, so an increase in intake with the short grass. This is our maize-based rations, long maize and short maize, again, sorry, short grass silage along with maize. So again, we can see that increase. Milk yield was higher in cows when they were fed grass silage along with maize silage, so these two, but it was also higher in cows when fed a short chop grass silage compared with a long chop by around about 2 litres per day. So in a grass silage only based ration, it was higher, not really much difference under the maize silage based ration. Milk fat content, however, was decreased with a shorter material in both the grass silage-based rations and the maize silage-based rations. So it was decreased, but milk fat yield wasn't decreased. So we had a higher milk yield, slightly lower milk fat content, so the kilograms of fat produced per day was the same. Milk protein yield, however, was increased with a short grass material. And finally, we decided, well, we can't just look at the chop length of the grass silage alone. How does that interact with carbohydrate source? And we particularly wanted to look at the effect of starch in there. And North Americans feed quite high levels of starch, and we wanted to really push our UK diets and say, well, how much starch could we feed? So we went from about 10% starch in the ration up to 32% starch. Now, most rations in the UK wouldn't really have above 23 or 24% starch. So we really thought that this would challenge the cows. And we did that by feeding up to 4 kilograms of wheat and 2.5 kilograms of maize meal to achieve that. So we ended up with 4 rations, 2 based on grass silage. So this is grass silage with a fibrous concentrate, starch content about 12%, grass silage with a starch-based ration, with a starch-based concentrate at about 24%, maize silage-based forage with a fibrous concentrate at about 21% starch, and maize with a starchy concentrate, and this is now getting up to 32% starch. And this is what the physically effective fibre was within that. When we fed it to the cows, however, and this is looking at rumen pH, and I won't explain here what the different symbols are because you can see that really there is no effect here of the 4 different diets in rumen pH. It fluctuates throughout the day, but there's no real effect. And if we look at the main rumen pH, again, there's no real effect. And above, round about that 6.2 that we said was optimal. So there's no real negative effect, even when we fed those high levels of starch. And perhaps the reason for this was that these cows were fed individually, so they couldn't select from the diet of other animals. They only had their own diet. They were fed 4 times per day for this particular experiment, and they were fed ad libitum, so they weren't restricted. So all the things that we said previously in terms of the commercial practice, perhaps these were being counteracted here. In terms of performance, then the animals fed the maize silage-based rations, ate more and produced more milk, but there was no effect of the starch content. And in fact, when we looked at milk fat content, the milk fat content was actually higher when we increased the starch content here, increased those two. So really totally opposite to what you'd expect the effect of starch. We were feeding high levels of starch here. And in fact, this level of milk fat was similar in the maize versus maize and high starch concentrate at about 32% versus this one here at around about 10, 11%. They had a very similar starch content. So I'm just going to finish off by saying that rumen pH is affected by many factors making prediction difficult, and I think that's what creates a degree of confusion. Lots of people have opinions and will say what is affecting SARA or not affecting SARA, but often they don't have data to base that on. Because measurement of pH on farm and proxies such as rumen fill or fecal score or number of chews per bolus are all problematic. We do know that grass silage-based rations are considerably longer than maize silage or North American recommendations. We can't really give recommendations as to what the optimal chop length is, except from the limited amount of work that we've done is that there are a few negative effects on pH or performance from feeding quite a short chop grass silage, or indeed feeding higher starch. I would put a caveat under the higher starch in that we haven't really addressed the form of the starch in terms of how finely ground it is, because that can have a very major effect on rumen pH. So although we were feeding 32% without any negative effect, if we'd altered the starch, either form or how it was processed, it might have had a different effect. But we do know that there are issues on many UK dairy farms with diet mix consistency, that there is significant selection of components, not always for the concentrates. Some cows will actually select for the longer material, but nevertheless they are able to select, and underfeeding is prevalent on many UK dairy farms. So I would just like to finish at that point, and I'd welcome any questions and I'll try my best to answer them.
Thanks a million, Liam. That was a very informative presentation. We have some questions popping up already, but please keep on posting your questions because it's really important for you to ask whatever you want to ask to Liam. So we'll go ahead and start taking some time to answer them now. So the first question is, do we have a percentage for the UK prevalence of SARA?
No, most of the work has been done in North America. I mean, the closest would be some work that they did in Ireland a few years ago, but that was on a grass-based system. And most people perhaps wouldn't be aware that under a grazing system, and most of the work that I've been referring to has been based on sort of mixed rations. But of course, SARA is also an issue under grazing as well, because we've got a high sugar-based ration in terms of our grazed grass and a relatively low fibre content. Generally, the values that you see published have been from people who've gone round and taken ruminocentesis from dairy farms. Now, there are veterinary practices in this country who do that. I'm not aware if they've actually collated it and published it. I'd be very interested if they were, but it'd be a very interesting question. There are some limitations with ruminocentesis, and by ruminocentesis I mean that's taking a big needle and inserting it through the flank of the cow into the rumen and taking a rumen sample out. Obviously, you can't do that very frequently. You can end up with issues of abscesses in there, but you're also just taking it from one site in the rumen at one particular point in time. So it gives us a sort of snapshot of what's happening, but it doesn't necessarily tell us the whole picture. But it's better than nothing.
Okay, well, thank you. A second question is related to the diets. I think it was the third study. What was the sugar content of the 32% starch diet?
Yeah, a good question. I think it was, I don't think they were terribly different between all of them. I think the starch and sugars in that ration was perhaps around about 40%. So I'd have to check to see if you want to know exactly, then I can give you those. I don't have it to hand just now, but somewhere around about 10% or so. But no, I don't think it was much more than that.
Okay, thank you, Liam. Another question. Is your conclusion that particle size does not matter, or what is the minimum particle size you would suggest?
No, I wouldn't say it's not important. I think particle size is important, but I think that longer particle size grass silage doesn't seem to have a major benefit. And that major benefit is in terms of ensiling in the clamp. It can make the actual compaction more difficult. And certainly from our limited number of studies, and I would say that they are limited number of studies, we'd really like to investigate this more with different types of grass silage. So perhaps shorter chop length, more acidic grass silages would be of interest in there. So it's not unimportant. We are considerably longer than what North Americans have. But you could argue, well, in North America, 3.5% fat is, it would be quite a high value. We certainly don't want to be down at those low values for UK milk contracts. But when we were feeding our cows in the studies that we had, we were round about around about 3.8% to 4% fat. So there was a slight reduction in terms of milk fat content, but it wasn't a major component. The milk yield was increased, but the milk fat yield remained similar. So at this point in time, I wouldn't say that there's a major advantage to longer material. How short we would want that to be is another question. I would doubt that we want it as short as perhaps what North Americans have. But nevertheless, for a lot of farms, having that bit shorter probably isn't going to be a negative effect, and certainly doesn't seem to have the effect in rumen pH that many people would suspect it would have.
Okay, so we can conclude that particle size does not affect rumen buffering. That's another question.
No, it does affect it. Certainly if you get it to be very short, so if you have got a very high maize silage-based ration, then you can be into the levels where it could be having an effect. So again, forage particle size is important, but we just don't have enough data just now. All that we can say is that we are quite different to North America, and that North American guidelines aren't really suitable. That may partly be to do with the way in which we measure it, because our wetter grass silages mean that when we look at the total ration, you can get concentrate ingredients, particularly things such as soybean meal or rape meal, can actually just attach and cling on to onto the wetter forage, and they don't get into that bottom pan. Now that doesn't mean to say that they are effective fibre, it just means that the method isn't perhaps very good. And maybe we need to look at modifying that method a little bit for the UK as well. So perhaps we may need to do the forages separately from the concentrates and then sort of add the two together rather than trying to do it as a total mixed ration. Because I feel that we may be overestimating some of the forage particle length on some farms because of the very wet forages. But nevertheless, I don't think that's the major overriding factor. We do have a lot longer grass silage. Maize silage, as I said, isn't an issue, but if we have a very high maize silage-based ration and we feed a lot of concentrates, then we could end up having issues as well.
Okay, thank you. The next question is, did your work find an optimum duration for mixing a TMR?
It's a very interesting question, and the answer is no. We would certainly like to come back and revisit it. We had roughly a similar proportion of tub mixers versus paddle mixers versus auger mixers. We didn't find any significant difference between any of those three, but there was so much variation between individual farms. And certainly speaking to some other people, 60 minutes, they would say, well, they know farms who actually mix it for longer than that, particularly if they go and have the breakfast before they come back and feed. We can't say an optimum time. Most manufacturers would tell you what that should be. They would tell you what sequence it should be, but I'm not sure under what evidence they've actually based that. But I think the sequence that we put it in and how long we mix is quite important, because we can over process as well as under mix as well. And sometimes if you mix things too much, things can start to come out of the mix and you can end up with a poorer mix as well. So I think it's a very good question. And I think we don't really have an awful lot for that. Certainly the manufacturers of the mixer wagons would have some information. I'm not sure under what evidence that's actually been based. But over mixing can be as bad as under mixing.
Okay, we now have a question on the same note. There was a large variation in mixing times on your survey farms. Is there any evidence that dyes can be overmixed? Also, where does wet mixing fit in here?
Yeah, well, I think the answer is yes, that over mixing things can start to come out. I think by wet mixing, you'd probably mean compact feeding, which is a method of feeding that was being developed in Denmark, where you soak the concentrate ingredients, preferably overnight, and then you mix them in with the forage components. And that provides more of a kind of mash to the cows. So rather than a ration that they can select out, it makes it more difficult from that point of view. I think there are logistical problems in doing that in terms of how many mixes you have on the farm and how many different groups you may have, and the volume that you have to wet the night before. And the evidence for it does suggest that you end up with a more consistent ration to do that, but I've not seen any convincing results to show that that can be translated necessarily into cow performance. But certainly, I think it is a means to try and reduce the diet selection, and I would suspect that where there have been benefits to compact feeding, that's probably been because as a group the cows have had a more consistent ration, which is what we want them to achieve. We want every cow to get the same diet in the morning, the afternoon, and all the way through to when they're fed the next day. We don't want some cows getting more concentrates, and we don't want some cows to be underfed. So anything that can reduce that can be important, but I think we maybe need a little bit more work to see how the mixer wagon itself, and whether there are differences between, I'm not speaking about makes of mixer wagons, but specific sort of design types in terms of paddle or tub mixers or auger mixers, whether they are all the same.
Okay, good, thank you. Another question. Are there any data from boluses looking at rumen pH in the grazing cow through the day and relating this to forage availability as the paddock is grazed down through the day?
Yeah, there has been studies. The Irish have done more on this, and there can be as much fluctuation in rumen pH in cows that are grazing. Obviously the sugar content in the grass is grazing during the day. There are times of the day when cows will graze more, so when they're turned out in the morning they'll graze, but often they'll then have a period where they'll lie and ruminate before grazing in the late afternoon and evening. So all of those are introducing feed at different times. The sugar content is higher in the afternoon, so there is quite a lot of variation. Although we showed the variation in pH under that mixed ration, there can be as much, if not more, under a grazing ration as well. And obviously that will depend on how tightly you graze in terms of the composition of the diet as well. So rumen pH is just as important for grazing animals.
Okay, thank you. Another question. Was there a difference in texture among the grass silage in the trial rations, like more stem or more leaf?
No, it was exactly the same field. When we went out, we chose a field, and basically one swath would be chopped at the short chop length, the next swath would be chopped at the longer chop length. So we tried to randomize that across the fields. So it's not one field that was receiving the short and one that was receiving the long. They were within the same field, and within the same field, we tried to make sure that we weren't one half of the field was one treatment and one half was the next. What we wanted to determine was the only difference would be the effect of the chop length. So in theory, they should be exactly the same chemical composition going in. Now, when you come to feed out, obviously the shorter chop material has a different texture in its own right because it's shorter chop, but the chop length also affects how well you can compact it, and that can affect the fermentation within the clamp as well. So as you saw from the slide, there was more lactic acid in the short chop material, and that kind of indicates that perhaps it was more acid production and more consolidation within that. So it's always a sort of a double effect of the chop length. We want to look at the effect of the chop length on cow performance, but the chop length also affects the ensiling ability as well.
Okay, thank you. Another question is, was the digestibility of the fiber per se measured in the trial?
Yeah, we did. In both studies, we measured the digestibility of the fiber. The fiber digestibility was less with a shorter chop material. And we feel that might be part of the reason that the shorter chop material was residing in the rumen for a shorter period of time and was passing out and that might have been reducing the digestibility, but the net effect was that the cows were eating more and they were producing more milk. So yeah, the longer chop material, because it was longer, was staying in the rumen for longer because it couldn't leave. It had to be broken down by the rumen microbes more. That meant the cow was eating less and producing less milk, but because it's staying in the rumen for longer, it's actually being digested more. So that's quite a common feature you find of altering the particle size, is that longer particles stay in the rumen for longer, and therefore they tend to be more digestible because they've been in the rumen and they've been attacked by the rumen microbes. But the net effect on cow performance is that the cows often eat less and produce less milk as a consequence.
Thank you. Another question: what will be the optimum NDF percentage in a TMR or PMR ration?
Yeah, it's a good question. It's difficult because I think we need to look at the physically effective content. Generally, most rations in the UK would be round about 35 to 36%. Plus or minus a couple of percent either side. But really what we've been trying to look at is not just the fibre content. So you could have some of that fibre coming, say, from soy hulls, which is present there as a concentrate. Now that provides fibre, but it doesn't provide effective fibre or physically effective fibre. So what we are looking at is not just the fibre content within the ration, which is what we have traditionally looked at, but the combination of that fibre content and its physically effective attributes as well. And round about that kind of 15 to 20% of physically effective fibre appears to be the optimal level. But in our rations that we looked at, with the grass silages that we looked at, we were somewhere between 25 and 30% physically effective NDF. So it's just trying to not just characterize the fibre content, which is what we're used with, and perhaps in the future we might be looking at the physically effective fibre to try and combine not just the chemical composition but the physical attributes as well.
Okay, thank you. So we're nearly close to the time. So the last question is, what rate of refusals do you recommend to feed, and where do you recommend those refusals go?
Yeah, it's a good question. It's a difficult balance to get. When we're doing a study, we tend to have between 5 to 10%, but obviously that means that you are throwing away or you're not feeding between 5 to 10% of the diet, including the concentrates. And that can make TMR feeding more expensive. I think heifer rations would be an obvious site for that. Perhaps the lower yielding cows. Difficulty in incorporating very large amounts within dry cow rations because principally the mineral content, specifically calcium, can sometimes be unbalanced. But somewhere between 2 to 5% if you manage it well and it's consistent. It depends how much variation you have within your group size and variation from day to day. But if you have a very consistent feeding regime and a pretty consistent group size, then you can get as low as kind of 2%. But of course, that 2%, if that 2% refusals is just the sort of stems or stalks from your maize that the cows don't want to eat, again, that's not really refusals. That's the bits that the cows don't want to eat. And what we want is refusals to be the same composition as what the cows were fed. So if they're refusing the sort of poorer material, then again that indicates that it's some degree of selection going on. So the composition of those refusals is important. So it's a difficult balance between the two. I think if I was doing it commercially, I wouldn't want to be much above 5%. I think it would be difficult to be much below 2% without running the risk of leaving a substantial amount. And feeding it to something like heifers would be the most perhaps obvious way of doing it. But dry cows, if there isn't very much, might also be possible.
Okay, thank you, Liam. We're approaching the closing time, so a final reminder before we close. The recording of this webinar will be available to watch back on the AHDB Dairy YouTube channel in due course. All of those that have registered will receive an email alerting you when this is live on the website. A big thank you to all of you for listening. We've had a great turnout and participation of the webinar, very good questions. So thank you again for your participation. And of course, a very special thanks to Liam for taking time out of his schedule to deliver this very interesting webinar. Thank you all and have a good night.